Okay, all right. I know it's the afternoon. Thank you so much for showing up. It's the last session. I'm really excited you guys are here. We'll try to make this worth your while. My name is Nikita Raze, and joining me today is Anurag Bharti. And we'll be talking to you about how we supercharge our sales intelligence using Databricks. And let's get started. A little bit about me. My day job is building and scaling large-scale data systems that power DigiCert's AI and analytics. When I'm not chasing down pipelines, I am chasing chickens in my backyard, hiking with my dogs, or just managing the chaos of life right now with 2 little kids. That structure and unpredictability of that life is something I bring into how I think about data systems at work. Anurag, you want to talk a little bit about yourself?
Yeah, hi. So my slide is a lot more muted than the previous one. That's because I'm more introverted in nature, and my job is as a data engineer. So I like to read a lot, especially about health, nutrition, and scalable systems. And as expected, I would watch documentaries on YouTube and wherever I find them. Since I'm from India, I like to watch cricket. I used to play before, but not much now. And got a little bit curious about hydroponics, which is basically soilless farming. So thank you.
All right, thanks, Anurag. Before we jump into the project, I wanted to take a few minutes to talk about who are we as a company. So what is DigiCert and what it is that they do, right? DigiCert is a digital security company. We essentially provides a lot of certificate, encryption, and authentication services, right? Our goal is digital interactions that you guys have in your day-to-day lives. We want you to feel secure about the privacy, the authenticity, and also the compliance part of it. We secure, this is just to give you a sense of what it is that we secure. So we secure everything from AI agents to software, devices, content, medical devices, and everything in between, right? So you can imagine the amount of data that generates. And to put a number to it, we help secure about 28 billion web connections every single day. Our goal with this project was, how can we get that data and actually make it useful for us, right? So it's not just stored, it's not just visible, but it's actually useful for us to take strategic decisions on. And that is how CCE was born. Now, before we talk about the project itself, I wanted to give you a sense of what was holding us back. Why didn't we try this 2 years ago or 4 years ago? Well, the answer is we did try. This is the 3rd iteration of our project. The first 2 we tried were on-prem and AWS, and it didn't really pan out back then. What was holding us back is the data that we have, the telemetry data, is incomplete and fragmented, so it's distributed across different systems. It's on-prem, some of it is in cloud, some of it is, believe it or not, still in CSVs, and we have to reach out to people to send it to us. So obviously, all of this made the analysis very inefficient, a lot of manual effort, and much more errors possible, right? We lacked real-time insights because all of these systems were refreshing at different rates, and then we did not have a single source of truth. So you ask the same question to 5 different people across 5 different departments, like, how many certs did this account issue today? And you get 5 different answers. And so, with Databricks, we were able to go from in this fragmented world to a focused, centralized system in a matter of months. Without it, we would still be, putting together all these data sets with a patchwork of tools, and we would still be, trying to fight scale and losing time instead of actually using this data. Okay, so that is why we built CCE. CCE stands for our Centralized Certificate Events Platform. Essentially what it does is it consolidates all of this telemetry data into a single unified system. Originally built as a compliance project, we found several applications in our sales and go-to-market teams. Originally, it was built for proactive compliance monitoring, outlier and anomaly detection, and then the 3rd use case we have is sales intelligence, and we were able to generate opportunities from this as well. How does CCE transform the game, right? Like I said, it's essentially pulling together all of this certificate events data from all of these different systems. We are unifying it, and we're making it available for additional analysis, right? What this did for us was it helped us provide complete market visibility, right? Which means that we would know in an instant, at the moment it happens, like who issued what, when, to whom, and by whom. This is the data that's very crucial to our sales teams. We were able to automate a very manual and error-prone process, And we were able to provide real-time data for strategic decision-making, which meant that our sales and operations teams could actually action on the insights within the window of opportunity. With Databricks, we were able to build all of this system once, and you were able to scale it as our use cases grow from time to time. Okay, challenges. So building something like this isn't easy. We had our fair share of challenges. A couple that I want to point out. So one of the core principles of this project is being able to poll public APIs. We poll over 42 different public APIs. We have no control over the reliability or the response time on these APIs, right? So being able to poll them in a reliable and scalable manner was crucial. We get anywhere from 10 to 90 million records through these public APIs every single day. And the deduplicate, like the duplicate number of duplicates is unknown, right? So we can't say that it's 50% duplicated or 10% or maybe 100%. So being able to deduplicate at scale was crucial as well. And obviously, as you can imagine, we generate a lot of data. So being able to structure the tables in a way that not just the reads, but also the writes were fast enough. And this is our key constraint, which is basically zero reprocessing, means when the data point enters our system, we never want to process it again. And Anurag will talk to you a little bit more about why that was crucial, but it's mostly to do with cost. Building something like this meant we had to rethink our entire engineering process. So, from how we ingest to how we store to how we process and everything in between. So how did we do it, right? This is a high-level architecture. This architecture is built, it's a standard architecture built entirely on top of Databricks. We use from ingestion all the way to the analytics, right? So we use Delta Lake, Spark Streaming, and we also use Databricks dashboards for this. With Databricks, we were able to build a modular architecture, and as our use cases grow across sales, compliance, and product, we are able to scale it out as needed. With that, I'll hand over to Anurag, who's going to talk to us about the architecture in detail.
Thank you, Nikita. In this slide, I'm going to just mention about how the high-level workflow goes. And so the main point over here is that we use Databricks recommended medallion architecture. So we do have the bronze layer over there, which has the raw data that we ingest straight away from the internet. The silver is a little bit of clean data, and the gold is what we expose to our end users. So the middle layer is where we use Spark structured streaming. In the bronze layer, we use regular Databricks jobs, and the last layer is we use structured streaming for that, but it's a much less simpler version of what happens in the middle. So I'm going to just zoom into. So you can clearly see there are 3 stages over there: bronze, silver, and gold. And I'm just going to zoom into each, and I'm going to just talk a little bit more about each stage. So this layer is, so we have 40 plus APIs, and this layer has only one task, which is to download the data from these APIs and store it as is in the bronze layer. There's just one transformation that I do, which is the addition of a partition column over here. And apart from that, we just store it. What we get is what we store in the bronze layer. And the task is simple, but if you look at the project overall cost, this one stage itself costs 47% of our overall costs. So, and I'll explain why it is so later. So this layer also is pretty simple as far as objective is concerned. Since we are pulling data from 40 APIs at the same time, there is a very good chance that the same data can show up in multiple APIs. So we do end up getting 3x or 5x or even 7x of the same data again. And that duplicate can come in next second, maybe after a week, 1 month, 3 months, whenever. This layer does only one task, which is to deduplicate the data, no matter when we get, whether we get it to the next instant, or we get it after a month. The deduplication should happen as it is supposed to be, and that's what this layer does. Simple task, but this layer itself costs us 50% of our entire pipeline. And the last layer is really simple, hardly anything to do over here because we have clean data in the silver. So all we have to do is we go to our stakeholders, get the logic from them, apply it using Spark, and store it in the gold layout over here. And this is what gets exposed to our stakeholders. As far as cost is concerned, just 3%, so not much. It's not that complex, and cost-wise also it's pretty efficient. So yeah, that's about it. And now that you have at least an overview of what each stage does, I'm just going to get into what kind of challenges we faced per stage. So as I mentioned, this layer has just one objective: ingest the API data in a reliable and consistent manner. Reliable means, regardless of the error, if it is the API server going down or whatever error it is, don't miss the data. Get it in the next scheduled run. That's the meaning of reliable over here. And consistent is download the data. So don't download so many copies of the same data that we end up deduplicating a lot. Just be in consistent way. So that's the whole objective that we do over here. And one of the main challenges in this layer is cost efficiency. Since we have 40 plus APIs that we download from, we just need to do it in a cost efficient way. So what we do over here is we use multi-threading, and we use one Databricks job with just one driver, and that does all the downloading and all the saving into the final bronze layer. If we take a driver, let's say it has 4 cores, we take a multiple of it as far as threads are concerned and download it in a multi-threaded way, store it in our bronze layer. And that's why this layer, that's why we are able to achieve cost efficiency, because it's just one driver which is doing everything for us over here. One of the challenges in this layer is getting rate limits. Since I'm downloading in a multi-threaded way, you can have so many threads pulling data from the same API, and often they happen to cross the rate limits. So to slow down that, what I have done over here is I've built in exponential backoff into the code itself. So whenever the rate limits exceed, the exponential backoff kicks in and it slows down, it pauses all the threads. So, and once we are within the limits, they just resume. So this way there is no error. Usually if you try to download so much, you get error 429, which is too many calls, I think. So to prevent that, the exponential backoff helps us a lot, so we don't cross the rate limits. And the next error that we see here is API server error. So when you're downloading from the internet, the server that is serving you the data can go down. And it can come up in a matter of minutes, hour, 2 hours, 5 hours, I don't know. It's not up to me. So what I do to fix this error is I use Databricks jobs, and all these APIs run in a scheduled manner. Let's say, for example, the schedule is once an hour, and in hour 0, I get an API error, which is, I think, 500 code. So if I get that error, I just kill the job there itself. And the next schedule run, I start the same downloading of data again. If I get an error again, then I kill the job again, and then the next schedule run. This way, there is zero manual intervention. Even if I'm on holiday, I don't have to worry about it. It'll just do its task. And usually, this error resolves soon. Yes, sometimes they do take a few hours, but regardless of it, there is no manual intervention. It's just automated, and that helps a lot as far as having an automated manner is concerned. Otherwise, I would have to have one of us log in and check, and I just didn't want that. So that's how we solved the problem over here. And the last is offset tracking. Since we have 40 APIs, and each API gives a lot of data, you don't want to re-download the same thing. Then you'll have 1,000 copies of the same data point, and neither do you want to miss any record. If you miss it, then again, your stakeholders won't trust your data. They'll just say you're just downloading some random thing, which doesn't make sense. So how do we do that is we use delta tables to capture all the offsets per API. And assume we had 1 million data points to download. All these 1 million is chunked into 0 to 100, then 101 to 200, 201 to 300, and so on. We download these chunks. If a chunk fails, we retry it in the next scheduled run. So we do have all that logic built in. Again, no manual intervention. The code takes care of itself. And I'm here delivering a speech. I don't really have to worry about my pipeline because I know it'll just work the way it is. And if something goes crazy, I do get alerts for it. Usually that doesn't happen, but errors don't happen because there's a lot of auto checks built in to the pipeline. So it will just run as is. The next stage, it's just got one task, just deduplicate, that's it, as simple as that. But this is the most complex, and as per me, this particular stage decides the viability of the project, because no matter what project you have, if it's not going to be within the cost, it'll never work. No one's going to use it. So so deduplicating at scale is the objective, really hard. And this is what and some of the problems that we see in this layer is small file problem. Since I'm using multi-threading, there'll be several threads downloading the data and storing it into our target table. So what happens is a lot of files get created in the bronze layer. In the keynote, we heard about delta tables. So delta tables internally use Parquet files. So as you download more and as you save more, there's just a lot of files going to get accumulated at your source. And that's a problem, because when my job starts, assume I downloaded 1,000 files, I have to open and read those 1,000 files and then start parsing the records. And that's not efficient. Reading and parsing 1,000 is not really efficient. You need to compress them. How do I do that is what I'll explain, but that's one challenge in this layer. The next one is growing size of target table. So we download about 90 million per day average. So in 10 days, that's about 1 billion. And by experience, when you have large tables to do an upsert query on, initially it'll be fine, but then gradually that upsert query will take forever to finish, and the cost will just blow out of proportion. So how do we fix that? I'll get into that. So that's one challenge that we see over here. And the next one is the variable incoming volume. Whether I get 50 million data points in a day, or 100 or 200, I don't want to see memory error. I don't want to see out of memory or CPU getting crazy. I don't want to see that. So how do we solve that problem? That's one. Regardless of the incoming volume, the pipeline should just work. So that's one challenge that we had in this layer. So, and before I get into the solutions that I use to solve this, I'm just going to explain what are the tasks that I do in this particular layer. It's just one job that runs, and it does three things. The first thing that it does is it reads X number of files from the source. So at source, these are all Parquet files that get saved. So we read X number of these Parquet files from source. That's the first thing that happens. Second one is we do some minor transformations on the files that we have loaded from source. And the last is inserting into a target table using the merge command. We do an upsert, and in Databricks, it's called a merge command. If the data is already present in the target table, don't do anything. If it is not present, then insert. So that's the merge command that we use to insert into a target. This ensures that there's always one copy of a given data point. So these are 3 tasks that we do per run, per loop. And what is the first thing that I do? Okay, yes, these are the tasks that I do, but what is the first thing I do? I run an optimize command, and that solves my small file problem. 1,000 files with 5 records each. What optimize does is it compresses them into 10 files of 500 rows each. So instead of reading 1,000 files, I only read 10. And that's far more efficient and saves a lot of time. Databricks also does optimize for you automatically, but that's not enough for my use case. So that's why I always run an optimize command as the first thing that when the job starts. And since the files are compressed, it's just way more efficient. Batch size is the single most deciding factor in the viability of this project. And batch size is nothing but how many files are you going to read from the source per loop or per iteration. That's what batch size tells you. There are 2 flavors of it, max files per trigger and max bytes per trigger. I use the files per trigger, but you can also use the bytes per trigger, but the logic is the same. how many files you're going to read from the source per loop, or how many MB or GB of data you're going to read from the source per loop. That's the only logic as far as batch size is concerned. But this is the most important factor that decides how quick your job will run and if it's going to be efficient or not. And that batch size solves my growing size of target table problem. It solves my variable incoming data problem, volume problem. I'll explain later how as I get to it, but and for the growing size of target table, I use partitioning to solve that problem. So since I'm doing an upsert or a merge query, in a normal unpartitioned table, I will be reading the entire target table while doing the upsert because I have to find the ID. I don't know where that ID is existing. Because both my source and target tables are partitioned, I only read that exact partition instead of the whole table. And our tables are pretty big. In the previous slide, we mentioned they are 75 terabytes plus. I don't have to read the whole thing. I just have to read one partition where I'm going to be doing an upsert on. So that helps with growing size of target table. And now I mentioned batch size is the most important factor, and it's a tunable factor that you get in structured streaming. I'm just going to show here what happens. Okay, since it's a tunable factor, how do I know that whatever batch size I've given is right or wrong? So the default batch size is 1,000. So I increase it to, let's say, 1,500. And then I go into the executors page, and I check, did anything fail? If yes, then I see a lot of red over there. Those are your failed tasks, and those tasks have failed because they got out of, those executors failed because they went out of memory. I don't want that. Because every time an executor goes down, it'll slow down the whole thing because then you have to bring up a new executor, all that has to happen. I don't want that. It'll slow down my overall execution and make the whole process expensive. So that's what I check. If I increase the batch size from 1,000, which is default, to 1,500, I go and check have my any executors failed. If not, I'm good, then I increase it a little more. What I also check is, this is the metrics page on your Spark cluster. This is how I would like it to be. The first graph is CPU, second is your RAM usage, and the third is your disk swap utilization. Everything is consistent. There's no spikes. So I don't want this. The CPU is all over the place. The disk space, RAM is also all over the place. And you can see a little bit of swap. It's the worst thing to have when you are working with Spark structured, because if you get even one failure, you have to restart the whole job. So basically, you're paying 2 times the amount to do the same processing. So I want to avoid that. So this is how I check if my batch size is well or not. If I find some out of memory or anything going out of how I would want it to be, I just reduce it, and it's a tunable parameter, so you just need to keep tuning it. There is no thumb rule for it. I just use these to figure out if I'm okay or not. And the last stage is the simplest one, but before proceeding, since I just spoke a lot, and as per me, it is a little bit confusing, but if you have any clarifications, I'm open to take any questions now. Okay, moving on. So the last stage is where we expose the data to our stakeholders. In the previous layer, now we have clean data, which is deduplicated and ready for use. And in the previous layer, if I get this duplicated data at the right instant, or if it comes after a week, or after a month, or even after 2 years, it doesn't matter. Because I'm using an upsert query using partition columns, it will work as expected with no duplicates, and that's how I fix the problems over there. And now in this stage, the objective is to build a base data set so our stakeholders can use it in their downstream reports. And it's got 2 challenges. One is to be flexible towards the evolving business logic. So we use Spark streaming over here, but the code has been modularized. So if a particular mapping has changed, it's very easy to swap it out. You need to keep in mind that when you're building any streaming or even a batch pipeline, just modularize it. So if the business logic changes tomorrow, all you need to do is just swap out that particular component, not the whole code. So that's how this is flexible towards business logic and allow for optimized reads. In all the previous layers, I just wanted my writes to be fast. But here, since it's a read-heavy layer, I want my reads to be fast. And it has to be fast because our tables are pretty big over here. It's got billions of rows. And it's always growing. So how do we allow for optimized reads? There's a delta table setting that you get. And it's called data skipping num indexed columns. What that does is it captures, the default setting is 32, which means the first 32 columns of your delta table, the metadata for it is getting captured. The average and things like that get captured. So when you give a filter where age is less than 10, the delta table knows in your large table which particular section to go and search the data for. It's not going to search the whole thing. That's how your reads get quicker. So we use this a lot. However, if you increase this a lot, then your metadata increases, then you have a lot of storage to do. You don't have to do it, but at the back end there is. And that storage leads to increased costs for you. So what we do is we put it to much lower. I think it is at 7 or 8. That's what we use. So we capture the metadata for the first 7 or 8 columns. And those are the important columns that our stakeholders use to filter data on. So that's how our reads are quicker over here. And yeah, thank you, Nikita. Over to you.
All right, thanks, Anurag. To finish up, I mean, it's a good project. It's been working great for us, but obviously we want to improve on it, right? So what are we looking at? First and foremost, conversational AI. That's what the whole conference has been about. So we're totally working on this. We're working to see how we can get this information out of the hands of analysts and engineers and put it in the hands of our sales team so they can ask natural language questions directly and don't have to wait on an analyst or an engineer to give them the insight. We are working with Genie mainly to be able to create an app that can do this for us. And then the second thing that we are focused on, and it's kind of the 2 and 3 combined together, is we want to optimize our pipeline as much as possible so we can enable that real-time search. We have another app built on Databricks apps, which basically helps our end users, this is sales and marketing teams, actually search through this data set at scale. But it's not quite real-time yet, so we want to make it more robust so we can get to that real-time search. But yeah, that's it. That's our project, and thank you so much for your time. Thank you. We'll take any questions. I know the quest is over, but if you can please take the survey so we can present next year again. Thank you.
Thank you.